Welcome back. In this video, you will learn about the direct comparison test for series. Let's get to it. All right, so far you have seen a couple different tests for convergence of a series. We have seen the p-series test, the geometric series test, and the integral test. And for each of those tests, the terms of the series that we are testing needed to be pretty simple and have specific special characteristics in order for the test to be applied. And so if there are any slight changes from those characteristics in a series, those tests that we have been using no longer apply to the series. We cannot use them. So for example, here we have a series that we can recognize to be a geometric series, right? We have 1 divided by 3 to the power of n. This could be rewritten to just be 1/3 to the power of n, and so the common ratio would be 1/3 for the geometric series. R would be equal to 1/3. And since that is less than 1, we know that this geometric series converges. However, if we slightly change this series, let's say we have n in the numerator instead of 1, all of a sudden we have a series that is no longer geometric. This is not a geometric series, and so we can't say if this converges or diverges using the definition of the convergence of a geometric series. For another example, here we have a series that is a p-series. We have 1 divided by n raised to a power of 4, and so for the p-series, p is equal to 4, and since p is greater than 1, we know that this p-series would converge. However, if we were to add 1 to the denominator of that series, right, we have 1 divided by n to the 4th plus 1, this is no longer a p-series. We can't say that p is equal to 4 and that this series converges because it's no longer a p-series. Once you add that constant to n to the 4th power in the denominator, this no longer has the special characteristics that a p-series has. And then one more example. Here we have a series that we could use the integral test for. This series would meet the requirements of using the integral test, and this would be a good series to use the integral test for because the corresponding function to this series would be easily integrated. We could use u substitution because the denominator, if we set it equal to u, n squared plus 5, the derivative of that would be found in the numerator, right? The derivative of n squared will include n to the 1st power, and so that is found in our numerator. And so we could determine the convergence of this series using the integral test. However, if we just change that n from being to the 1st power in the numerator to being n squared, we no longer have a series that is easily integrated, and so the integral test isn't as nice to use, even though this series would meet the requirements of using the integral test. And so with all three of these examples here, you can see how we can have a series that is very similar to a series that we do know the convergence of, but we can't use those tests because they have slight variations of those series that make those convergence tests not applicable. And so what can we do for series like these three over here that don't meet the special characteristics that we look for in each of these convergence tests? Well, what we can do to get around this is use two other types of convergence tests known as comparison tests. We're going to look at the first one of those comparison tests in this lesson, and we'll look at the other one in the next lesson. And what these tests are going to allow us to do is compare a series that we don't know the convergence of that has more complicated terms to a series with simpler terms whose convergence we know. In other words, what we're going to be doing is looking for similar features in our series that might look like a geometric series or a p-series or maybe something that we can easily integrate. All right, and so that leads us to the comparison test we are going to look at in this video, which is the direct comparison test. And so here's what the direct comparison test allows us to do. Let's say that we have two sequences, b sub n and a sub n, where b sub n is greater than or equal to a sub n, and both of those sequences are greater than 0, meaning that both of the sequences have all positive terms. All right, so b sub n is the bigger sequence, meaning all of its terms are larger than a sub n, and a sub n would be the smaller sequence, all of its terms are smaller than b sub n. All right, so keep that in mind, but then for these two sequences, if the series for b sub n, the larger sequence, converges, then the series for a sub n, the smaller sequence, also converges. If the series for a sub n, the smaller sequence, diverges, then the series for b sub n, the larger sequence, will also diverge. Okay, and so it's important to remember that this only works in one direction. We can only say that if the larger series converges, then the smaller series converges, and if the smaller series diverges, then the larger series diverges. We cannot say the reverse. We cannot say that because a smaller series converges, that the larger will converge as well, and we cannot say that because a larger series diverges, that the smaller series diverges as well. This only works in one direction. All right, and so essentially what is going on here is the series that we want to determine the convergence of will either be the smaller series or the larger series. And what we're going to do is compare that series to a series that we do know the convergence of. We can either find a larger series that converges, and so then our series will converge as well, or we can find a smaller series that diverges, which means that our series would diverge as well. And so that's where the direct comparison comes into play. All right, and so before we look at some examples of using the direct comparison test, I want to show you visually with a graph why these statements are true, why the direct comparison test works. All right, so here we have two graphs that I want to look at here, and we're going to start by looking at this first graph. And here we have the terms of the bigger series b sub n. And as you can see, the terms of this series are getting closer and closer to a specific value. And so this bigger series converges. And so if we were to look at a second series, a smaller one, a sub n, that series would have no choice but to also converge to a specific value, right? All of the terms of that series need to be less than the terms of b sub n, because this is a smaller series. And because of that, those terms will also converge to a specific value. If we were to instead pretend that that second series or the smaller series diverges, and each subsequent term gets increasingly larger than the previous, well, all of a sudden, we have terms of a series that are larger than b sub n, and we can't have that because the series a sub n needs to be a smaller series. And so these terms can't diverge. They cannot get larger than b sub n, right? And so this is not possible for a series that is smaller than another series. If the larger series converges, then the smaller series must also converge. All right, now if we look at our second graph here we have a smaller series that diverges. As you can see, each term is getting larger and larger. It is not getting closer to a specific value. Each term is getting larger towards infinity. And so if we were to have a larger series, b sub n, each of those terms would need to be bigger than each of the terms of the smaller series. And so this would represent the series b sub n, right? And so since the terms of the smaller series keep getting larger and diverge, they don't settle at a specific value, the terms of the bigger series also have to get larger and larger. If we were to instead say that the larger series converges, let's say that the series starts out larger, but then eventually, if those terms are going to converge, those terms are going to be smaller than the terms of a sub n. And so this series, b sub n, would no longer be a larger series. In order for this series to be larger than a sub n, each of those terms needs to be larger. And so we can't have a series b sub n that is larger than a sub n where the terms converge. They always need to diverge, just like the smaller series. Okay? And so in conclusion, if a larger series converges, then we know for a fact that the smaller series must also converge. And if the smaller series diverges, then we know that the larger series must also diverge. All right, and so this was a visual representation of why the direct comparison test works and why we can use it to determine the convergence of series that are similar to series that we know the convergence of. All right, and so with that, let's take a look at some examples of using the direct comparison test to determine the convergence of a series. All right, so here's our first example. For this series, we have the sum from n equals 0 to infinity of 1 divided by 3 to the power of n plus 5. Now, the first thing you always do when you have a series that you want to determine the convergence of is, of course, use the divergence test. All right, so you would take the limit as n approaches infinity of 1 divided by 3 to the power of n plus 5, and if that wasn't equal to 0, you would know that the series diverges. All right, but for this video, we're going to be looking at examples of series where the divergence test is inconclusive, where the limit as n approaches infinity of our expression is going to be equal to 0, which tells us nothing about our series. Okay, so always keep that in the back of your mind. Always try the divergence test first before you try any other convergence test. All right, but just know that for the examples in this video, the divergence test will be inconclusive, and so we will need to use another test. All right, and so if you look at this series here, we have 1 divided by 3 to the power of n plus 5, and so this doesn't quite match any special form of a series that we can test the convergence for. We could try to use the integral test, but integrating this expression won't be very easy, and so we probably don't want to do that. And so what we can do instead is compare this series to a series whose convergence we do know. And so what type of series could we compare this series to that we do know the convergence of? Well, notice that we have 1 divided by 3 to the power of n. That is a feature that is very similar to what we find in a geometric series. And so what we can do is compare this series to the sum from n equals 0 to infinity of 1 divided by 3 to the power of n, right? If we just remove that plus 5, we now have a geometric series. This would be equal to the sum from n equals 0 to infinity of 1/3 to the power of n. Right? This would be the same as 1 to the power of n because 1 to the power of n is just 1, and so we could just take that whole fraction to the power of n, which is what we have right here. And this is in the form of a geometric series that we can easily determine the convergence of. We have some value raised to the power of n, and so that value is the common ratio r, and so r is equal to 1/3. And remember, for a geometric series, if that common ratio is less than 1, which 1/3 is, then we know that this series converges. And so this geometric series we know converges, and we're going to compare this series that we know converges to a series that we don't know the convergence of. And so before we can make any conclusions about whether this series converges or diverges based on this series we're comparing it to, we need to show that 1 divided by 3 to the power of n is greater than 1 divided by 3 to the power of n plus 5. Right, so if we compare those two sequences whose terms we are summing up for the series, we will have 1 divided by 3 to the power of n plus 5 and 1 divided by 3 to the power of n. Whenever you have very similar expressions where the denominator of one expression is larger than the other denominator, you know that that expression will be less than the other expression, because a larger denominator means that the value will be smaller, right? If you compare 1/5 to 1/4, 1/5 is equal to 0.20 and 1/4 is equal to 0.25. The denominator of 5 is larger than 4, but the decimal value of 1/5 is smaller than 1/4. And so this applies to all fractions. When the denominator is larger, that fraction will be smaller than the other fraction. And so we can say that 1 divided by 3 to the power of n plus 5 is less than 1 divided by 3 to the power of n. Okay? And that's going to be true for all values of n greater than or equal to 1. No matter what value of n we plug in to either of these expressions, this expression is less than this expression. All right, and so since 1 divided by 3 to the power of n plus 5 is less than 1 divided by 3 to the power of n, this series right here is our smaller series, and this series is our larger series. We know that this series converges, and so we have a larger series that is convergent that we are comparing to a smaller series. And so what we can say is that since the larger series, the sum from n equals 0 to infinity of 1 divided by 3 to the power of n converges, then the smaller series, the sum from n equals 0 to infinity of 1 divided by 3 to the power of n plus 5, must converge as well. Okay, so that's what the direct comparison test allows us to do. Because we found a series that is larger than the series we are looking at, and that series converges, we can make the conclusion that the smaller series converges as well. And so this right here is the final solution to this example. We can make the conclusion that our series converges. Okay, let's look at another example. All right, so here's our second example. For this series, we have the sum from n equals 1 to infinity of 1 divided by 2 plus n to the fourth power. All right, now for this series, the divergence test would be inconclusive, so we don't know anything based on the limit as n approaches infinity of our series. And then additionally, none of our other convergence tests can be used for this series, right? This series is not a geometric series. This series is not a p-series, although it does look very similar to one, and we'll get back to that. And this series, although it may meet the requirements for the integral test, we may not know how to easily integrate this expression. Having 1 divided by a denominator of 2 plus n to the fourth power is not really an easy expression to integrate, and so we're probably not going to want to use the integral test. And so what we can do is compare this series to a series that we do know the convergence of. And like I said earlier, this series looks very similar to a p-series. We know that a p-series will have 1 divided by n raised to some power. And in this case, we have 1 divided by n to the power of 4. We just have this constant of 2 being added to it that makes things a little bit difficult. And so while this may not be a p-series, we can compare it to a p-series, right? So let's compare this to the sum from n equals 1 to infinity of 1 divided by n to the fourth power. We just remove that extra 2, and now we have a series that is a p-series whose convergence we know. The value of p is 4, right? The power of n is 4, and so for the p-series, p is equal to 4, and because p is greater than 1, we know that this p-series converges. Right, for a p-series, when your value of p is greater than 1, the series converges, but when the value of p is less than or equal to 1, it diverges. All right, and so now we have a series that we are comparing to our original series that converges. All we need to do to make the conclusion that this series also converges is show that this is a larger series. That because we have a larger series that converges, that our smaller series must also converge. All right, so if we compare our two series, we have 1 divided by 2 plus n to the fourth power and 1 divided by n to the fourth power. And so can we say that our original series is smaller than the series we are comparing it to? Well, if we look at the denominators of our two expressions, this is similar to our last example, our original series has a denominator of 2 plus n to the fourth, but the series we're comparing it to just has n to the fourth in a denominator. And so this denominator is larger than this denominator because we are always adding 2 more to the value of n to the fourth. And so no matter what value of n we are looking at, for all values of n greater than or equal to 1, this expression will be smaller than this expression, right? When you have a larger denominator, that value will be smaller than the other value. And so we can say that 1 divided by 2 plus n to the fourth power is less than 1 divided by n to the fourth power. And that will be true for all values of n greater than or equal to 1. All right, and so now we have shown that our original series will be the smaller series, and the series we are comparing it to is the larger series. And so since the larger series converges, then we know that our smaller series must also converge. All right, so via the direct comparison test, we can say that since the larger series, the sum from n equals 1 to infinity of 1 divided by n to the fourth converges, then the smaller series, the sum from n equals 1 to infinity of 1 divided by 2 plus n to the fourth, must also converge. Okay, and so that is the final answer to this example. We found a larger series to compare our original series to that converges, and so since that larger series converges, we know that our smaller series must also converge. Okay, let's look at one more example for this video. Okay, so here's our last example. For this series, we have the sum from n equals 1 to infinity of 1 divided by the square root of n plus 1. All right, now just like our other examples, if you were to start out with the divergence test, this series would be inconclusive. We don't know if it converges or diverges. And then just by looking at our series, we can already see that it's not a geometric series, it's not a p-series, and it's not an expression that we can easily integrate, right? We have 1 divided by the square root of n plus 1. That's not a very easy expression to integrate, and so even though this series might meet the requirements for the integral test, we're probably not going to be able to use it. And so we need to find another way to determine the convergence of our series. And so what we can do is compare the series to a series whose convergence or divergence we do know. And so if you look at the structure of our series here, we have 1 divided by the square root of n plus 1. If we remove that plus 1, we would have 1 divided by the square root of n, which would be in the form of a p-series, right? So if we compare that to the sum from n equals 1 to infinity of 1 divided by the square root of n, that would be equal to the sum from n equals 1 to infinity of 1 divided by n to the 1/2 power, right? The square root of a value is the same as taking that value to the 1/2 power. And so we have a p-series of 1 divided by n to the power of 1/2. And so p is equal to 1/2. All right, and so since that value of p is 1/2 and that is less than 1, then we can say that this p-series diverges. All right, so when the value of p is less than 1, the p-series diverges. So this series diverges, and so in order to make that same conclusion about this original series, we have to show that this new series that we're comparing it to is smaller than the original series, right? In order to say that your original series must also diverge, the series you're comparing it to needs to be smaller. It's the opposite of when you're trying to show that a series converges, right? In our previous examples, our series converged, and so in order to show that the original series converged, that new series needed to be larger. But now we want this series to be smaller to prove divergence for our original series. And so if we compare our series, we have 1 divided by the square root of n plus 1 and 1 divided by the square root of n. Just like with our previous examples, if we look at the denominators, since the numerators are the same, we have the square root of n plus 1 and the square root of n, and so this denominator will always be 1 larger than this denominator, right? And so since this expression will always have a larger denominator, the value of that expression will always be smaller. And so 1 divided by the square root of n plus 1 is less than 1 divided by the square root of n. And so the series we are comparing our original series to is larger than our original series. And that's not what we wanted, right? In order to say that our original series also diverges, the series we are comparing it to needed to be smaller, but this one is larger. And so we can't make that conclusion that this series also diverges via the direct comparison test. At least not if we compare it to this series. We can still show that this series diverges. At least that's what we think is going to happen, since it's so similar to this series. We need to pick a different series to compare it to that also diverges, but its terms are smaller than the original series. All right, so we kind of have to restart here. We need to pick a different series that will meet the requirements of the direct comparison test in order to make a conclusion about our original series. And so instead of choosing the series of 1 divided by the square root of n, let's just remove that square root, and let's see if we can compare it to just 1 divided by n. All right, that's also fairly similar to our original series. Okay, and this series is going to diverge just like the previous series that we used as a comparison, right? This is still a p-series, except in this case, p is equal to 1 because n is being raised to a power of 1. And since p is equal to 1, we know that this p-series diverges, okay? So we know that this series diverges, and what we're hoping for here with 1 divided by n is that this series will be smaller than our original series. And the reason I choose 1 divided by n is because n should always be larger than the square root of n, right? And so at some point, that plus 1 isn't going to matter, and this denominator of just n will be larger than the square root of n plus 1, which means that these terms will be smaller than these terms since that denominator is larger. But we have to show that that is true. That's what I'm hoping to be able to show, so that we can also conclude that this series diverges but we have to compare our terms first. And so if we do that, we want to compare 1 divided by the square root of n plus 1 to 1 divided by n. And so what we want to do is determine which of these two expressions is smaller than the other. And the best way to go about this is just to look at the first couple terms. Because the denominators differ more than just a constant, right? Before we just had the square root of n plus 1 and the square root of n, but now we have the square root of n plus 1 and just n. So they are different, and so it's harder to compare them without actually looking at a couple terms. So let's start by looking at n equals 1. What is going to happen when n equals 1? Well, we'll have 1 divided by the square root of 1 plus 1 and 1 divided by 1, right? This would be the value of this term, and this is the value of this term. Now, 1 divided by the square root of 1 plus 1, that is 1 divided by 1 plus 1, which is 2. So we have 1/2, and 1 divided by 1, which is 1. So if I erase this, we have 1/2 and 1 is greater than 1/2. Okay, so the term from our new series is greater than the term from our original series. Now if we look at the second term, n equals 2, we will have 1 divided by the square root of 2 plus 1 and 1 divided by 2. Now the square root of 2 is approximately 1.4, and so 1.4 plus 1 would be 2.4, and so this denominator is 2.4, and that is a larger denominator than 2 for 1/2, all right? And so this value will be smaller than 1/2. And so for n equals 2, the term of our original series is still smaller than the series we are comparing it to. But now let's look at n equals 3 and n equals 4, and something interesting is going to happen. When n equals 3, we will have 1 divided by the square root of 3 plus 1 and 1/3. Now the square root of 3 is approximately 1.7, and so 1.7 plus 1 is 2.7, and so this denominator is approximately 2.7, and that is a smaller denominator than what we have over here. We have 3 versus 2.7, and so since 3 is a greater denominator, that term is going to be smaller, and so now the inequality sign flips. We went from having our original series terms less than the series we are comparing it to having the original series term be greater than the series we are comparing it to. And that's going to hold true for n equals 4 as well. We'll have 1 divided by the square root of 4 plus 1 and 1 divided by 4. The square root of 4 is 2, so 2 plus 1 is 3, so our denominator is 3, and so we have 1/3 and 1/4, and 1/4 is smaller than 1/3. And so, from here on out, if you were to look at more and more terms, the terms of our original series are going to be greater than the terms of the series we are comparing it to. Okay? And so if you want to check that out for yourself, you can look at n equals 5, n equals 6, and so on. But starting with n equals 3, this term will be smaller than this term. And so what we can say is that 1 divided by n will be less than 1 divided by the square root of n plus 1 for values of n greater than or equal to 3. Okay? And so what we have just shown here is that the series that we are comparing to our original series is the smaller series for values of n greater than or equal to 3. And so that might seem a little problematic at first because it's not smaller for every single term. However, it is going to be smaller for most of the terms. Besides n equals 1 and n equals 2, this series is smaller than this series. And so in the long term, for all values of n from 3 to infinity, this series is smaller. And so we don't care about those first couple terms, we can ignore them. In the long term, this series is smaller than this series. And so since this series is smaller and it diverges, we can conclude that our original series also diverges. All right, and so we can say that since the smaller series, the sum from n equals 1 to infinity of 1 divided by n diverges, then the larger series, the sum from n equals 1 to infinity of 1 divided by the square root of n plus 1, must also diverge. All right, and that is only because we showed that the series we are comparing our original series to is smaller for the long term compared to that series. All right, and so that is our final solution to this example. We have concluded that our series diverges because we found a series to compare it to that is smaller than it, and that series also diverges. Okay, and so with that, this was the last example for this lesson video, but if you want to see more examples of using the direct comparison test, feel free to check out my examples video that I'll have linked at the end of this video as well as in a description below. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.